Yeah, we have, we have several checks we can use. Right? We have several theorems and several checks.
Yeah, because I think that we find that we have bad Lie brackets at some point.
There's bad Lie brackets, yeah. Bad Lie brackets may rule out controllability, and you may still have controllability, right? You need to check what bad brackets are these, and we have several checks at the end of the lecture that we discussed small time local controllability. Was it lecture 10? Or, I don't remember. So, you just need to try these checks. And nothing more. It's okay. Any other questions?
Regarding problem 2, I don't even know how to start.
Problem 2, well, this is, it's almost nothing from this course, it's just, you'll play with this differential equation. So you have one control and you need to get to this point. And so you may chop you may have, say assume 3 intervals. So from 0 to T1, T1 to T2, T2 to T3. These are 3 unknowns, the 3 T's. And the value of the control over each of these intervals are another 3 unknowns. So it's as if I'm doing piecewise control. So I have 6 unknowns, and I don't think the problem would need 6 things to play with, to manipulate. I don't think the problem would need more than that. So if you try this differential equation, you can integrate, you can get the flow, right? You can get the flow along F and along G for a constant U, right? You can get the flow easily. This differential equation is not that hard. You can get the flow, and when you get the flow, then you can, using the first control U1, you can flow to get the first point, and then the second point, and the third point. Each have the same flow, just different U. So at the end of the day, the final point, you will equate it with 0, 0, some number, and you have many things to satisfy these 3 equations, right? You have like 6 tables. Maybe you can do it in two intervals, I'm not sure, but I'm sure that 3 intervals would really suffice. So yeah, it's nothing on this course. It's an educational example that when you apply the control in reverse, you should see what you get. So yeah. Any other questions? So the lecture is already long. Yeah, you got it. Very good. So, differential geometric control theory. So far we have been concerned with these types of system, x dot equals f of x plus summation some control inputs 1 to m gj of x uj, what we call the control affine systems. And in a differential geometric language, we know how to cast, we already casted the system, right? We said, well, x lives in an m manifold. The f and gj's, they all live in the vector fields. They are vector fields on the manifold. If this is, say, equation 1, so a solution of 1 for us is an integral curve, right, of these vector fields. Integral curve, gamma, that maps some interval in the real line, the time to the manifold, such that it satisfies the differential equation. So gamma prime of t is f composed with gamma of t plus this summation uj gj composed with gamma of t for all t, right? So we had a language. It was a little bit hard to build this language. I believe you guys are mastering this language now. You will not be intimidated if you see this language in papers. And we will keep doing more of the same. But what were the benefits to us as control engineers from this language? Do we get any benefit? Well, we got Frobenius, right? Because having this language, we got some useful theorems. So Frobenius integrability, we got this. We got Cho orbit theorem, right? So which was very useful in analyzing nonlinear controllability for nonlinear systems. It is the only tool available in literature to analyze controllability of nonlinear systems without linearization. Either you use linear algebra, which fails in several cases, or the only other alternative is just this theory. And based on that, we got some useful algorithms for motion planning. And we will get more towards the end of this course. So the list will continue. But today I'd like to have a special case of this class of systems, of this equation one. I want to focus on the special case of mechanical systems. What do you mean by mechanical systems? I mean systems that come from from mechanics, applying equations of motion. So they are typically on the form mass times acceleration plus some centripetal and Coriolis forces. They are equal general forces on the right hand side, right? Mass times acceleration equal forces. Obviously, if I have the system 2, I can write it on the system 1 and apply the same tools, and this is what we're going to do. But when you do that, it's as if you're applying the tools that we learned above on a special structure. So you will make use of that special structure to obtain results that are useful here. But first of all, we need to make sure that we have enough language to cast this system like we did above. So obviously I can say that the configurations live in a configuration manifold, that's fine. I can say that the pair configuration and velocity lives where?
Tangent bundle.
The tangent bundle, right? And if you move forward right away, you will struck with the acceleration. So your acceleration q double dot lives where? This is an issue. Well, we expect that the acceleration, like velocity, they are vectors, it should live in the tangent space. And this is what we need to focus on today. Where does the acceleration live? What do you mean by an acceleration of a curve? Okay? And we'll take a simple example like we did in 241, but with more details today. So this example, that is a curve from 0 to 2 pi to R2. Okay? So this is my curve. Gamma of t. So here is the real line. That's okay. So this is t, the direction of t. And this is the map gamma that maps t to gamma of t. Okay? At any point here, say this point, P, in some neighborhood, I can have a local chart. I can map this guy to the Cartesian R2, right, which is x and y. I can map this guy to the polar, which is r and theta, correct? So, and we know that, so this is, say, psi as a coordinate chart, this is phi as a coordinate chart. we know that there is a map here between the two. So I can go from here to there, say F1. What kind of map is this? I have a point from here to there. So this is phi inverse, and then I'll compose with epsilon, right? So this is epsilon phi inverse. And vice versa, I can do the following. I can map here. So this is F2, which would be phi composed with epsilon inverse. And just for the sake, not to make it a big deal, I'll write one of these. What is F1 to go from xy to r theta, right? So r theta is actually F1 of x and y. This is super easy. We know that transformation already, right? Square root x squared y squared, tan inverse y over x, where x is not zero, okay? So I have these maps back and forth. Okay, so here is the definition of my curve. So the curve as a function of time in the Cartesian coordinates is cosine t and sine t. This guy is just revolving along the unit circle. Over there, it's, when you do it the way you like, you get, it's a constant radius and theta varies linearly in time. Okay? So how do you compute your velocity vector? The velocity vector is very easy, straightforward, and transforms well under coordinates. It lives in the tangent space, and you simply compute it by the derivative with respect to time in any coordinate system, because it lives in the tangent space. It's coordinate independent. So this is negative sine t, cosine t here. And indeed, in this space, if this is your curve, you can check that this vector in this space is tangent everywhere, okay, to the curve. Because it's the unit circle, it should be normal to the point itself. So if you dot this guy with gamma itself, you get 0. So indeed, it's tangent to the surface. And it's very obvious here, for example, because this will be 0 and 1. In that space, the curve is simply this guy. This is the curve. This is gamma of t, right? R equal 1 and theta goes linearly. And this vector 0 and 1 is always tangent to the vertical line. It's tricky, right? But more importantly, I can transform this guy to that guy. How? Because I know that there is a transformation here, F1, right? So if I know the transformation between the points, then what is this transformation between the velocities? What's that? What's this transformation? Between gamma primes? What's the transformation?
Tangent map, push forward.
The push forward, the Jacobian, simply, right? If I have a transformation, you just get the Jacobian. And it's linear transformation, just the matrix, right? So I multiply this guy by the Jacobian matrix, get this guy, and vice versa. I can do it the other way around. I have here F2, for example. So here I can map by F2 star, the Jacobian, right? Okay, so velocity is defined very well. When we go to the acceleration, I don't know how to define the acceleration yet, and I'm suggesting to compute it just by the intuition, just differentiate one more time. And here we will get cosine t and negative sine t. Here we will get 0 and 0, the 0 vector. Obviously, there can be no linear transformation to map this guy to that guy. No linear transformation, right? You can't have a matrix such that when you multiply by 0 vector, you get something non-zero, right? So no linear transformation. So obviously, the double derivative doesn't live in the tangent space. It doesn't transform well under change of coordinates. Which raises the question, how to define the acceleration of a curve? What is the acceleration of a curve? We discussed this, like I said, a bit in the 241 course. We will discuss here in more detail. What is the acceleration of a curve? First of all, why the double prime doesn't work? Right? why this thing doesn't work. Let's see. How do you define your double prime kind of thing? So this is gamma double prime of t is the limit as h goes to 0 of what? This is the derivative of gamma prime. So it's gamma prime of t plus h minus gamma prime of t divided by h. Correct? Okay. This guy lives where? Lives where?
The tangent space at gamma of t.
The tangent space at gamma of t of your manifold. And this guy lives where? The tangent space at gamma of t plus h, right? So if this is your curve gamma of t, say this is t, here is the underlying t, here is t plus h, right? This is the tangent space at t, this is the tangent space at t plus h, possibly it's a different tangent space, it doesn't, at t plus h. So these guys live in different tangent spaces, and I cannot simply add and subtract vectors that they live in different spaces. You cannot, you cannot add a vector in Cartesian to a vector in polar. So what is the issue here? So we need to connect nearby tangent spaces, right? We need some form, some mathematical tool that connect these guys. Nearby tangent spaces. And from this statement, we expect something that does connect. So we're gonna call it a connection. This is where the name comes from. So we're seeking a connection that connects nearby tangent spaces, okay? Okay. Actually, we encountered this before. We encountered this problem before. Do you remember when? We were also differentiating a vector. So when did we differentiate a vector in this course? We just did it once. The rebracket, because it's the derivative of it, right? So we were differentiating along a vector. So this was not just a curve, it was the flow actually of that vector field, because we were differentiating along the vector field, it has flow, so this was the flow. So if this is a flow and if this is a map that maps points, this is not a map that maps points. This map, this is a gamma of t, it's a curve. It maps this guy to points in the map. It doesn't map this point to that point. The flow does map this point to that point. So if you have a map, you can use its inverse. Right? So if this is your vector, for example, here, I can use the push forward of this map, correct, to transfer it here. And this is my original vector, say, gamma of t. So let's use red here. If I have a flow, if I have a map, I could have done this, and we indeed did it before with